Chapters 22 and 23 deal with geometric optics. So we're going to be dealing with how light interacts with different materials, right, as it passes through different media, and we're going to focus on two different types of objects, mirrors and lenses, in chapter 23. So in these two chapters, we're going to model light as a ray. So light does this weird thing. It behaves like a wave sometimes, and it behaves like a particle sometimes. But as far as geometric optics are concerned, we can just model light as kind of like a vector, right? Just a straight line. So a group of, or a bundle of light, we can model as a ray that has a direction. And so that's why we deal with it in terms of geometry and trig, because it has very nice linear properties. So when light interacts with matter or some material, it will react four different ways. So it can reflect off the material, it can refract into the material, so we're going to be dealing with refraction a lot. It can scatter, which means different frequencies of the light will refract at different angles, and then it can be absorbed. So the energy that the light ray has actually gets transferred into the material. The two primary interactions we're going to be dealing with in chapter 22 are reflection and refraction. So we're going to focus on these two types of interactions, and then in chapter 23 we're going to deal with how mirrors reflect light and how lenses refract light. So what happens when light passes through a medium that's not air? It slows down. So the original, or the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So we're going to use that for the speed of light in air, because it's very, very close to the speed of light in a vacuum. And so all of these materials, water, glass, plastic, so all these materials will slow light down. And the ratio by which they slow them down we call the index of refraction. So for a vacuum and air, we take it as 1 because it doesn't slow light down at all. So c is the speed of light. If you divide it by the speed of the light in that medium, you get some ratio larger than 1, and that's our index of refraction. Alright, so c is 3 times 10 to the 8. The speed of light going through that medium is lower, so it's always going to be 1 or greater than 1. And so these are common indices of refraction that we're going to be dealing with. Usually we deal with water, oil, glass, plastic. We can use 1.59. So these are our indices of refraction. This is basically the ratio by which these materials will slow light down. So the first thing we're going to talk about is reflection. We got a really nice formula, really easy one to use. The law of reflection says that if an incident ray strikes a reflective surface at an incident angle, theta I, the angle of reflection is going to be equal to that incident angle. Now keep in mind, when we deal with reflection and refraction, these angles that we're measuring them from a line that's perpendicular to the surface. So this is my normal line, it's perpendicular to the reflective surface. Theta incident and theta reflected are both being measured from that normal line. So they're not being measured from the surface, we're measuring them from the normal line. I've probably said that 500 times in my life, and I still make that same mistake on occasion. So we just got to be really careful when we're labeling our incident angles when a light ray is hitting a surface, making sure that we're drawing that angle with respect to the normal line. So let's do a basic reflection problem. We've got two mirrors that are perpendicular to one another. right? So this is mirror 1. The formula is not going to be our challenging part. The most challenging part is drawing the diagram to kind of reflect what's happening and labeling our angles, and then using, you know, geometry, trigonometry, wherever it's applicable, to solve for something, either an index of refraction or an incident reflected angle, something like that. So this incident beam is striking mirror 1, and it's striking mirror 1 at a distance 1.25 meters from where these two mirrors meet. So I expect this light beam to hit mirror 1 here, and then reflect, and then strike mirror 2, and then reflect again. So we've got two occurrences of reflection right here, 1.25 meters from this corner here. I expect it to reflect and then hit the mirror 2 up here, and then reflect again. So our incident angle is 30 degrees, and we have to determine the distance the reflected light travels before striking mirror 2. So they're asking for the distance between this point right here, where the beam initially hits mirror 1, to the point up here where it strikes mirror 2. So we're looking for that straight line distance. So I'm expecting that I'm probably going to have to use some trigonometry, right? Because that looks like the hypotenuse of a right triangle, right? And I already have one side here, 1.25 meters. So I'm going to have to probably use a trig ratio or something like that. Part 2 says, in what direction does the light ray travel after being reflected from mirror 2? Now we have kind of some freedom as to how we want to describe that angle, but we're talking about directions, so just like vectors, you know, an angle with respect to some surface or some axis is the best way to describe that direction. So I drew a picture, kind of a 2D picture, like we're looking at the scenario like this, right? We're looking at it in that direction. So here's my incident angle. Figures are typically not drawn to scale, in my case, because I'm pretty bad at drawing, but this is 30 degrees, okay, and it's striking mirror 1, a distance 1.25 meters from where the two mirrors meet. So I'm going to use that law of reflection and say, well, if this angle is 30 degrees, this angle also has to be 30 degrees. Theta incident equals theta reflected. So I'm looking for this distance. I labeled it lowercase d right here. So I'm looking for that distance. So I have a right triangle. I have one side, right? I have what I'm calling the adjacent side. Now if you wanted to use this right triangle right here, you could. That would be fine. You would just have to use sine, because this distance right here is 1.25. But what I did was I took theta 1's complement. Okay, so this is theta incident, that's theta reflected, but they're both equal to 30 degrees, so I'm calling it theta 1. So here's theta 1. I know theta 1's complement, which I'm going to call phi 1, is 60 degrees, because this is a 90 degree angle right here. Okay, this is the normal line that's perpendicular to the surface of mirror 1. So phi 1 is 60 degrees. I'm going to use that as my reference angle. Use that as my reference angle. I have the adjacent side. I need the hypotenuse, so I'm going to use the cosine function. So cosine of phi 1 is equal to the adjacent side over the hypotenuse. So cosine of phi 1 is equal to 1.25 meters divided by d. That's what I'm looking for. So I can multiply both sides by d, divide both sides by cosine of phi 1. I've got an expression for that distance I'm looking for. Cosine of 60 is 1/2, so that's a nice ratio. 1.25 meters divided by the cosine of 60 is 2.5 meters. And we could use the tangent ratio if we needed to find that h. I labeled it, we weren't asked for it, but that's good practice. You know, if you want to say like how high up the mirror does the reflected ray strike. Or you could find d first and then use the sine function, whatever you want to do. So we have some options there. But try and find h just for practice. Part 2 said describe the direction of this final light ray. Once it reflects from mirror 2, we're looking for the direction. So this is phi 1. This right here is a right triangle. So this has to be phi 1's complement, but I already know phi 1's complement. It's theta 1. I also could use that alternate interior angles are congruent, right? This is a perpendicular line to this surface, but mirror 2 is also perpendicular to the surface. So these two lines are parallel. So theta 1, they're alternate interior angles. So I draw another line that's perpendicular to mirror 2. So that's the normal line to my surface of mirror 2. And this is theta 1. This is a 90-degree angle. I know that's phi 1. So I'm using the law of reflection again to say if this is phi 1, this has to be phi 1 as well. Take phi 1's complement again, and I've got theta 1 up here. So I could say the light ray is traveling at an angle of 30 degrees measured from mirror 2. Something like that, right? So I could say, or 30 degrees above the surface of mirror 2, right? So like this. So theta 1 is 30 degrees from mirror 2, or from the surface of mirror 2. You could also talk about it in terms of phi 1, right? You could say it's traveling at an angle of 60 degrees from a line perpendicular to mirror 2, or normal to mirror 2. So there's a couple different ways you can describe the direction. Just as long as you're giving an angle, but you're also giving that angle with respect to either the nearest surface or the nearest normal line, something like that. So we have an idea of where that angle is. All right, so that's a basic law of reflection problem. We used it twice. We used it once here, and then you know, some trig and geometry sprinkled in there, which we all love. Okay. So we'll encounter reflection a few more times because there are two things that happen during refraction typically. So excuse me when I get these words mixed up. I always end up saying like reflection and refraction or something like that. So I'll try not to make that mistake. But when light refracts through a medium, right? When light refracts through a medium, when it goes through here, right? This is like a prism, a triangular prism. So light will actually pass through the prism, and the light ray will bend. So it will change its direction. It will refract through the medium, but then part of it will still be reflected. So we're going to talk about when it refracts and when it reflects and when it totally reflects, and we'll talk about those three scenarios. But now we're going to focus on refraction. So we're talking about the portion of the light beam that actually travels through that medium. Okay, so we've got a little bit of reflection, but in this prism we've got a lot of refraction. And we're going to actually do one, maybe two prism problems, or triangular prism problems, where the light refracts, travels through the entire object, and then refracts again. So we're going to have two different cases of refraction. So this is a diagram of a single incident beam that's hitting a surface. We've got that reflected ray. Okay, this is my theta reflected. Okay, my theta r. So what we do when we talk about refraction, usually we say theta 1 and theta 2. So we don't confuse it with the original theta r from reflection. So what was discovered is we've got this incident angle. The refracted angle, again measured from the normal line. See, this dotted line is the perpendicular line to that surface. This angle is different than this angle. And let's say this medium 1 was air, okay, with an index of refraction of 1, and this was water. Okay, so that's got a higher index of refraction, 1.33 I believe, off the top of my head. Don't worry about memorizing any angles of incidence. We'll have to either solve for it or we'll be given it in the problem. But we always have that table too here to refer to. Yeah, there you go. Water is 1.33. So we've got a higher index of refraction down here. And so we notice that if you're going from a low index of refraction to a higher index of refraction, this angle is smaller than this angle. And so what happened was, we look at the right triangle, right? If I were to take a line parallel to the surface connected to the normal line, I'd have a right triangle here. And if I did the same thing here with another line parallel to the surface, I'd have a right triangle here. So there was a pattern that was established that involved the ratio of the sides of these triangles. And they were proportional to the change in the index of refraction. Right? So traveling from N1 to N2 to a higher index of refraction. And so Snell's law was formed due to that relationship. Okay. So it's actually the sine ratio, right? So the opposite over the hypotenuse. So this ratio, or this relationship between the incident angle and the refracted angle, is related to the different indices of refraction for these two media. Okay, so it's N1 sine theta 1, right? It's all of the properties of one medium are on one side, right? You see the index, and then the incident angle is equal to the index of refraction for media 2, or medium 2, times the sine of the refracted angle. So this is Snell's law of refraction. Right? So our nice easy formula is for reflection, right? Reflection, and then Snell's law, this kind of more complicated looking equation, is for refraction. So we see that going from a low medium to a higher medium, the light bends towards the normal line. So theta refracted is smaller than theta incident. If we were to go in the other direction, if we were to go from a medium with a high index of refraction to a medium with a low index of refraction, the light is still going to bend, but it's going to bend farther away from the normal line. So that's a good way to check your work, right? If you're going from air to water, this angle should be smaller than this angle. If you're going from like glass to air, something like that, your refracted angle is going to be larger than your incident angle. So here is a glass block immersed in water. So we have water surrounding a glass block. Water has an index of refraction of 1.33, and glass has an index of refraction of, I don't know, I'll look it up. But we have two cases of refraction happening here, right? So we've got an incident beam here, it gets refracted, it travels through the block, and then it gets refracted again. So we're going to have to use Snell's law here, Snell's law here, and then sprinkle some trig and geometry in here, because we've got x, right? We've got the value of x, so we know the point where the original incident beam strikes the block. And we're looking for y. We're looking for this distance here, so there's a right triangle. And then it says the angle at which the ray exits the block. So I'm going to find both of these angles, right, because they're complements of each other. This is theta 2. Now the diagram kind of messes us up, because I want to use theta 1 here and then theta 2 here. But I'll work out some other notation so it's not too confusing. So we've got Snell's law twice. I'm going to find theta 2, and I'm going to find this angle's complement too, just so I can like describe the direction of the final refracted ray after it exits the block. So here is my diagram. I've got water. Water's incident or index of refraction is 1.33. Glass is 1.5. I looked it up, or I gave it to you in the problem, right? So again, don't worry about memorizing it. you do enough problems, you'll probably accidentally start memorizing it. Glass and water and plastic or and air are what we use most commonly. So I'm going to use Snell's law here. Right? They give me the incident angle. It's 43.8 degrees. So theta 1, this angle right here, is 43.8 degrees. So I'm gonna break the notation here just a little bit. I'm going to call this theta r. Right? So this is my first refracted angle. My first refracted angle. Okay. So Snell's law says the index of refraction of water. So I'm using W and G as subscripts to keep the two indices straight. So index of refraction for water times the sine of the incident angle is the index of refraction of glass times the sine of the refracted angle. So this is what I'm looking for. I'm looking for that first refracted angle. I know the incident angle and I know the two indices of refraction. So I'm solving for theta r. Solving for theta r. Divide both sides by the index of refraction for glass first. And so I have sine theta r on one side, but I don't want sine theta r, I want theta r. So I'm going to have to take the inverse sine of both sides. To solve for theta refracted, I'm going to have to take the inverse sine of both sides. So theta refracted is the inverse sine of this whole thing right here. The indices of refraction times the sine of the incident angle. So now I'm ready to plug my values in here. 1.33 for water, 1.5 for glass, and 43.8 degrees for the incident angle. When I calculate that, the refracted angle, the first refracted angle right here, is 37.9 degrees. So I need a little bit of information because I'm looking a little bit of extra information because I'm solving for y first, and then I'm eventually solving for that final refracted angle, right? That final refracted angle theta 2. So the first thing I'm going to do, I'm going to solve for y. So I've got this side. It's very similar to that first reflection problem. I've got this side that I want to be the adjacent side because this is my reference angle. This is the angle I want to use as my reference angle. We have some options here. That's just most convenient for me. That's my preference. So y is the opposite side. So I want to use the tangent function. I want to say tangent of phi refracted, phi sub r, is y over x, because I know what x is and I know what this refracted or phi refracted is. It's the complement of theta refracted. 90 minus 37.9 degrees is 52.1 degrees. So I'm going to use phi sub r and the tangent function to solve for y first. So tangent of phi sub r is y over x. Solve for y, multiply both sides by 3.66 centimeters, and plug in 52.1 degrees in for phi, and I get 4.7 centimeters. Okay, so that's y. Second question asks for theta 2, right, that final refracted angle. And again, I can find the new incident angle a couple different ways, right? Just like that first reflection problem, I can say alternate interior angles are congruent. So that's phi sub r, that's phi sub r. Or I can say this is a right triangle, so these two interior angles are complementary. By that reason, that's also phi sub r. Keep in mind, I want to use phi sub r as my new incident angle. Okay, not this one right here. I want to use this because it's measured from a line that's perpendicular to the surface. Okay, same thing here. I was looking for theta sub r up here. That is this angle right here, not this angle. So it's the angle measured from that perpendicular line to the surface. So I know phi sub r is 52.1 degrees. Excuse me, I'm going to use that as my reference angle and use Snell's law again. But now I'm going from glass to water. So I have to say the index of refraction, there we go, the index of refraction for glass times the sine of phi sub r, that's my new incident angle right here, is equal to the index of refraction for water times the sine of theta 2. And there's that theta 2, that final refracted angle that I'm looking for. So the algebra is very similar. Divide both sides by the index of refraction for water now. Take the inverse sine of both sides to get theta 2 by itself. So theta 2 is the inverse sine of the ratio of my indices of refraction. Notice they're flipped, right? So I've got n sub g over n sub w. Glass is higher than water. Up here, I had water over glass. So this is where Snell's law kind of makes itself a little more clear here, right? It's the ratio of the indices of refraction that causes that light to bend one way or the other, right? So water to glass, and then glass to water. So I substitute my values in, 1.5 for glass, 1.33 for water, 52.1 degrees for my new incident angle, and I have a final refracted angle of 62.9 degrees. 62.9 degrees from a line normal to the surface, right? Normal to the surface. Subtract that angle from 90, you get this angle. If you want to talk about it in terms of this angle, phi sub 2, whatever you want to call it, alpha sub 2, you can do that too. Just take theta 2's complement, and then that's that angle right there. Alright, so sometimes we'll have to, we'll know enough geometry about the situation and how the rays are being refracted inside of a medium as far as the angles, and we'll have to find the index of refraction of some medium. It'll be an unknown medium, and we'll have to find the index of refraction, maybe go back to our table and find out what type of material it is. So we've got a prism, and when we shine a light perpendicular to the surface, there's no refraction. Now the light does slow down in here, but there's no refraction, because the angle, the incident angle with respect to a line that's perpendicular is 0. Sine of 0 is 0. That means regardless of the particle's indices of refraction, there's going to be no refracted angle. So sine of 0 is 0. The left side of Snell's law is equal to 0, and the only way to make that a true statement is for the refracted angle to be 0. So we're not going to concern ourselves with this part right here. We're just going to talk about the laser beam passing through this prism and then refracting as it exits the prism. So this is one of those, physics problems where they give you an angle and it's like really tempting to use that, right? They give you a value and you're like, oh yeah, if I can just take that and throw it in my my formula or my law or whatever, everything will come out right. So this is a little misleading, right? This 22.6 degrees. If you notice, this line right here is not perpendicular to this surface. So this is not my refracted angle. Okay, it's not my refracted angle. So we're going to have to, I'm going to redraw this, and we're going to have to do some geometry around here to try and figure out what our actual refracted angle is. We're looking for the index of refraction, and we know it enters air. So we know the index of refraction out here is 1. So we're looking for the prism's index of refraction. So here's a drawing. It's a little bit nicer, right? I draw the beam as a single ray, and it strikes. So what's happening is it's perpendicular to this surface. That means it's parallel to this surface down here. So this line is parallel to the base of this triangle the whole time as it passes through. Then it strikes, and then it refracts at an angle of 22.6 degrees from the original incident beam, right? But if you see this line right here as it passes through, it's not perpendicular to this surface. So I drew a second line that passes through right here where the refraction is occurring, but I drew it perpendicular to this surface right here. Drew it perpendicular to this surface. And then, since that line is perpendicular to the surface, I'm going to use that as my normal line on both sides of the prism. Okay, see this normal line? So that means when this comes through, right, it's parallel to this line right here. So it's actually hitting at an angle of 60 degrees with respect to the surface, right? Because this whole triangle right here is a 30, 60, 90. I just made a smaller 30, 60, 90 with that laser beam. So that laser beam is the base of this small triangle right here, but it's still a 30, 60, 90. So this angle is 60 degrees. But that, again, that's not my incident angle. My incident angle is always measured from the normal line. Drew that normal line. It's normal, perpendicular, so it makes a 90-degree angle with the surface. I know this angle is 60. This has to be 60's complement. So my incident angle here is 30 degrees. So that's what I'm going to use in Snell's law. Alright, that's my incident angle, 30 degrees. Now I have to look at the diagram and determine what the refracted angle is, because it's not 22.6 degrees. It's the angle that this refracted ray makes with the normal line. Okay, so this whole angle right here is the angle that I have to find. So here's that geometry coming back to me. This is 30 degrees. Alright, this is a single line, this normal line. Okay, so we've got two lines. They're making what we call vertical angles. So this angle and this angle, they are vertical angles. Okay, vertical angles formed by two lines, they are congruent. So this angle right here is 30 degrees. And I'm looking for this entire angle right here to use as my refracted angle. So 22.6 degrees plus 30 degrees is 52.6 degrees. So this is my actual refracted angle, 52.6 degrees. My incident angle is 30. My refracted angle is the sum of these two angles, 52.6 degrees. I know the index of refraction for air, it's 1. And I know my incident and my refracted angles now. So I'm just solving for the index of refraction for the prism. So I have to use Snell's law. So the left side is the prism information, the index of refraction for the prism, and then the incident angle. The right side is for air, index of refraction for air, and refracted angle. I need to solve for the index of refraction for the prism. So all I have to do now is divide both sides by sine theta 1. Plug in my values. 1 for air, 52.6 degrees for the refracted angle, 30 degrees for the incident angle. The index of refraction for the prism is 1.59, which is good. We expect it to be higher because the refracted angle was larger than the incident angle. And it's a prism, and we're dealing with the other medium being air, so we expect it to be something, higher than air. Okay. So that's good. A lot of geometry, right? Take your time. Invest in a straight edge or a ruler or something. If you haven't done so already, it helps a lot. Try to redraw all the diagrams. Use pencil. I know that's not a very popular thing, but I use pencil whenever possible because I make a lot of mistakes. So redraw your diagram. We're seeing a lot of old geometry principles come back. Alternate interior angles are congruent. Vertical angles are congruent. The interior angles of a right triangle are complementary. Right? All of our trig stuff. So a lot of math, a lot of geometry and trig. Just take your time. Try to make diagrams as best you can. That'll help you identify all the angles that you're trying to deal with. Okay, so I think I've got time to maybe do the first half of this problem, because we're talking about angular dispersion through a prism. So visible light, white light, that is concentrated, in some prisms it doesn't stay white light. Okay, so the light ray will actually refract dependent upon the frequency of the light. Okay, so that's why when a white light hits a prism, that it will form a rainbow, right? Because all the light is being refracted, but they're being refracted at different angles because the frequency and the wavelength of different colors in the spectrum, in the visible spectrum, are causing different types of refraction. So we're looking for angular dispersion, right? We're looking for the angle between where the red light hits the screen and the violet light hits the screen. So it's not going to come out as one beam, it's going to come out as a spread of all the different colors in the visible spectrum. So for each frequency of light, there's a different index of refraction. So in this problem, they tell us the index of refraction for violet light is 1.66 and for red light is 1.62. So we're looking for basically a difference in refracted angles. Okay, now this diagram looks, pretty daunting, pretty intimidating, but my diagram, I'm going to try and clean it up. I'm not concerned with all of the light passing through at one time. I'm just going to use Snell's law for red and then use it for violet, and then I'm going to look at the difference in refraction, and that should give me the angular spread. So it says an equilateral prism of apex angle 60 degrees. What that means is the top angle here is 60 degrees. Right, top angle here is 60 degrees. They don't tell me if it's equilateral or even isosceles, so I don't know what's happening down here, but I do know that this angle, the apex angle, is 60 degrees. And the incident angle of the white light is 50 degrees. Okay, now that's going to be measured from a line perpendicular to that surface. So here is my picture initially. So I'm going to do, I think I did red light first. Yeah, so I did red light first and then I solved for violet. So I think I have enough time to at least get through Snell's law for the red light. The process will be identical for the violet light. Our values of our refracted and our incident angles inside the prism are going to change. And so that's what we're going to be looking at. We're going to be looking at the difference of values between our final refracted angle. So we know our apex angle is 60. We know it's coming from air. Okay, so we've got an index of refraction of 1 out here. For red light inside the prism, it's 1.62. For violet, it's 1.66. So we're going to do red light first, and we'll start at this surface right here. So the incident angle is 50 degrees. I drew a normal line on this surface, and then I also drew, I estimated my refracted beam, and I drew it all the way across the prism, and then wherever it strikes this side, I drew another normal line. Okay, so these two lines right here, these extra lines, those are my normal lines. Now the white light comes in like this, right? Kind of from down towards the bottom of the prism, it comes up like this. This is my refracted angle, or excuse me, my incident angle, sorry. Okay, so it's measured from that normal line. And then I know it's going from a low medium to a high medium, so it's going to bend towards that normal line, and so I drew it that way. Okay. Now here's the tricky thing too, because with this prism, the surfaces aren't the perfectly parallel or perpendicular to the way I'm looking at it. This is my first refracted angle. You see how this normal line goes like this? This is my first refracted angle. So when I use Snell's law at that first surface, That's my incident angle. That is my refracted angle. But I labeled this complement because I'm going to need this complement to get an idea of what's happening over on this side. All right. So theta 2 is my first refracted angle. So here's Snell's law. Index of refraction for air times the sine of the incident angle, which we know is 50 degrees, equals the index of refraction for the prism for red light, n sub r I'm saying, sine of the refracted angle. So I have everything I need in here to solve for the refracted angle. My end goal is to find theta 4 for both red and violet. So I'm solving for theta 2, that first refracted angle. Divide both sides by the index of refraction for red. And I had a little typo here. Should have used pencil, I guess. Take the inverse sine of both sides, right? Because I'm looking for the refracted angle. Take the inverse sine of both sides. Theta 2 is the inverse side of, here's the ratio of my indices of refraction times the sine of the incident angle. Plug my values in. 50 is my incident angle. 1.2 is the index of refraction for red. And I get theta 2 is 28.2 degrees. So let's go back up to the diagram and talk about how I'm going to use this information to find my new incident angle. Theta 2 was 28.2 degrees. 28.2 degrees. This makes a triangle. I don't know if it's isosceles or equilateral. It doesn't look like a right triangle to me, anything like that. But I do know that these three angles, 60 degrees, phi 2, and phi 3, all add up to 180. Because it is at least a triangle. So I do know that. I'm going to take theta 2's complement because this line is perpendicular to the surface. I'm going to take theta 2's complement and I'm going to find phi 2. So 90 minus 28.2 degrees is 61.8 degrees. So now I know this interior angle, I know all three of them have to add up to 180. So I'm going to find phi sub 3 over here using that property. Okay, phi sub 2 plus phi sub 3 plus 60 degrees is equal to 180. I found phi sub 2, which was 61.8 degrees. You can plug that in there, solve for phi sub 3, and you get 58.2 degrees. But my diagram tells me that this is phi sub 3. It's not my new incident angle. Okay, that's a very common mistake. That's not my incident angle. Theta 3 is this angle right here. So I've got to take phi 3's complement to find my second incident angle for this surface right here. So I found phi sub 3 was 58.2 degrees. 58.2 degrees complement is 31.8 degrees. Okay, so this is 31.8 degrees. I have a new incident angle. I'm going from the prism to air, so this is my incident index of refraction. Air is going to be my refracted, excuse me, my refracted index of refraction. So theta 3, theta 4, we're ready to use Snell's law again. I've got the incident angle, the refracted angle, I've got the incident angle, the two indices of refraction, and I'm ready to find theta 4. Okay, so this is my incident information, the red index of refraction, theta 3, my new incident angle, index of refraction for air, looking for the refracted angle. Again, the algebra is very similar. Divide both sides by n sub a, take the inverse sine of both sides, and get theta 4 by itself. So index of refraction for red was 1.62, air was 1, my incident angle is 31.8 degrees. So my final refracted angle, theta 4, and I'm going to give it another little subscript for red. Theta 4 for red is 58.6 degrees. So before I put the next video up, go through it. I know the solutions are there. Try not to look ahead. Whoops, no peeking. do the same thing for violet. Okay, so the process is practically identical. Alright, the only difference is we're going to use this for my index of refraction inside the prism. So it's going to be 1.66 rather than 1.62, but it'll be good practice. Go through it, draw the diagram on your own, and find this final refracted angle for violet. And with the next video, I will do the second half of this problem using this as my new index of refraction inside the prism, and we'll compare those refracted angles, and we'll be able to measure this angular dispersion. Okay, how much the red and the violet light are spread. Okay, all right, have a good one. See ya.